Hello everyone, this is chapter 11.10 where we'll be discussing Taylor and Maclaurin series. There's a lot of really fun stuff to talk about here. But to motivate everything, let's first start off with our usual power series that we saw from 11.8, but now represented as a function of x. And we're going to differentiate this quite a few times. Basically, we want to differentiate this as many times as we can, essentially infinitely many times. But let's just take a look at what happens. So first notice f prime of x is just now starting at 1 to infinity of c to the n times n x minus a to the n minus 1. And if you want to write it out, this is just c1 plus 2c2 x minus a to the 1 plus, I guess it would be 3c3 x minus a to the 2 and so on. So you see it gets kind of cluttered quickly, but you can tell what happens just term by term. Taking derivative term by term, we indeed get these things. Okay, good. So now the second derivative, just to show you, will now be the sum from n equals 2 to infinity, because notice every time we differentiate, we lose our constant term. So that's why the sum starts at, essentially the next integer in line now. So this is now going to be c to the c sub n times n minus 1 times x minus a to the n minus 2. And you can write out the list from there if you want to see how it expands out, which is nice. The only thing is, I want to now plug in values to actually eliminate a lot of this stuff. So let's first take a look at f. So notice when you plug in a lot of stuff goes to 0. In fact, everything goes to 0 except for c0. So here we just get c sub 0. Good. What about for f prime? Well, for f prime, when you plug in a, what do we get here? Well, here if you look at f prime, plugging in x equals a minus a is 0, a minus a is 0 here. So those go to 0 and we're left with c1. So it seems like we just get the constant that corresponds to that derivative. But it's not quite the case. Close, but not quite the case. Here, second derivative, we'll start to see something change a little bit. Now, I didn't write it out, but notice what we really get is just the first term, because our first term will always be constant. So our first term here is just plugging in n equals 2. And notice when you plug in n equals 2 here, we get 2, well, this is c sub 2, but that's going to be 2 times 2 minus 1, so it's just 2. And then here the power is 0, so we ignore the x minus a to that part. So really we just get 2c2. Similarly, if you were to take the third derivative and evaluate it at a, you will get something kind of similar here, only you get an n minus 2 coming down now, and then we start at 3. So if you plug in 3 to that, you'll get 3 times 3 minus 1, which is 2, times 3 minus 2, which is 1. So 3 times 2 times 1 is 6, c3, and so on. Now, as you go down this process, what you basically get is the following. The nth derivative of f evaluated at a, so notice the parentheses here in surrounding the n corresponds to the derivative. So that means how many primes there are, basically, equals n factorial times c sub n. And this will actually happen all the time. So this is the pattern, the general pattern we'll notice. And if we want to solve for c sub n, for our coefficients, we certainly can do that by just dividing. And we end up getting f, nth derivative of f, evaluated at a over n factorial. Which is great, because now what we conclude from this is that our function f of x is really the sum over, well, from n equals 0 to infinity, over the general term c sub n x minus a to the n. But now we know c sub n is really just this. So we kind of solve for it using derivatives, which is great. And then x minus a to the n, of course. And again, as far as radius of convergence goes, it's really just the same as the original power series, because f of x is defined to be a power series here. All right. So we have a really, really nice formula, and this is known as the Taylor series expansion of a function. Now, the Taylor series expansion of a function is just really the power series representation of a function using the fact that now we know how to find, well, the coefficients. So now what I'm going to do for you is I'm going to do a pretty traditional example, a pretty kind of typical example you'll see when introducing Taylor and Maclaurin series. Oh, by the way, Taylor series is this. So this is Taylor series. Maclaurin series is just a special case when a is equal to 0. So when you're centered about 0, then the Maclaurin series representation of a function is f of x equals the sum from n equals 0 to infinity of, notice when a is 0, you just get f, nth derivative of f anyways, evaluated as 0 over n factorial times x minus 0, so just x to the n. So that's all Maclaurin series is. So in fact, really that's kind of all we're going to see in 11.10, but I want to show you some examples so we can really see why this is so useful. So let's take a look at those examples right now. Right, so here we're given f of x equals e to the x, and we want to find two things. So first is Maclaurin series, which I think is kind of the fun part, and then it's Taylor series centered at x equals 2, which is a little more specific, but in doing one, we'll actually see what's going on here. So notice that we first need to find the function evaluated at 0, because remember, Maclaurin series means that the center is 0. So we need to do f of 0, then f prime of 0, then f double prime of 0, and then f triple prime of 0. By the way, since the sum is from n equals 0 to infinity, the 0th derivative is really just the original function itself. So you can think of this as f 0th derivative evaluated at 0. Now the kind of interesting thing here is that since the derivative of e to the x is itself, these will all be the same number. In fact, they're always going to be just 1. Since e to the 0 is 1, its derivative of e to the x evaluated at 0 is also 1. So by the way, how we normally get these is not just by looking at the first one. You have to actually find the derivative. So really, for good practice, I should just really be doing that. So not to confuse anyone, but if you consider the derivatives of f of x, we get e to the x for each of them. So it's always going to be the same. Then when you evaluate them at x equals 0, you get f of 0 is equal to e to the 0, which is 1, f prime of 0 is also 1, f double prime of 0 is also 1, f triple prime of 0 is also 1. In fact, in general, that's always the case. So really, f derivative of f evaluated at 0 is 1 for all n, as it turns out. So that means c sub n is just, well, that derivative expression, this guy, divided by n factorial. Perfect. And now, that means that our function's power series representation, which is just the Maclaurin series representation, is the sum from n equals 0 to infinity of c sub n, which is 1 over n factorial, times x to the n. And if you like, I'll actually write it a little better. I'll write it as this, x to the n over n factorial. And believe it or not, we actually saw this in chapter 11.8. I did an example of this, where we found the interval of convergence, and this actually converges for all values of x, believe it or not. You can show that by the ratio test. So in this case, the interval of convergence is negative infinity to infinity. So pretty cool. And that's the Maclaurin series expansion and interval of convergence. So I'll just box that all together. And this is really nice because now we know this is just e to the x. So if you want, if you plug in x equals 1, then you get the sum of 1 over n factorial, which we did an example of that before. We showed that was convergent in some section in chapter 11. But actually now we know that the sum, so kind of a consequence, let me just write that. A really, really, really nice consequence of this, I love these consequences, is when x is equal to 1, we get that e to the 1, which is e, is equal to the sum from n equals 0 to infinity of 1 over n factorial. So namely, that's 1 plus 1 over 2 plus 1 over 6. Actually, we need one more 1, don't we? Because 0 factorial is, I guess, technically 1. So yeah, we actually saw, so that example I was referring to previously in chapter 11, earlier on, was from 1 to infinity. But yeah, I may have not mentioned this, but 0 factorial is defined to be 1. And in fact, we kind of need that in order to even discuss Taylor series. So just let me note that somewhere. This is kind of a definition more than anything. But there is actually motivation as to why this happens. We're going to define 0 factorial to be equal to 1. So maybe not the best place to write it. Probably should have wrote it earlier on. But when we actually find these C sub n's, notice since our sum starts from 0, C sub 0 would have 0 factorial in the denominator. And don't freak out because 0 factorial isn't 0, so we're not dividing by 0. 0 factorial is 1. And if you want to look into why that's the case, there are really nice videos out there that talk about the motivation of this. And it's not super crazy as it turns out. I could probably discuss it right now, but I just don't want to take too much time. So sorry for that slight digression. But now let's move on to part 2 here. So we want to find the Taylor series of f of x centered at x equals 2. So we need to find the derivatives. We did. They're all e to the x. And then if you evaluate them at x equals 2, we'll get that the nth derivative of f evaluated at 2 is just going to be e to the 2, much like all these were e to the 0, which were all 1. Okay, good. So with that being said, now we can say that the Taylor series expansion of f of x centered at 0 is, well, it's going to be, let's see, it's going to be this over n factorial times x minus 2 to the n. And you can check for yourself as well to see what the interval of convergence is here. But this is actually true for all values of x as well. So the interval of convergence in this case is also negative infinity to infinity, but I'll allow you to verify that on your own. Again, you can just use the ratio test there, really. And it's not very difficult to do that. Perfect. So now we're going to take a look at the Maclaurin series expansion of some other special functions, kind of like e to the x. And yeah, I say Maclaurin series because really for Taylor series, this is all we're doing. So even though Maclaurin series is kind of a watered down version of Taylor series, I want to showcase that here in this video just so we can get used to that idea. And then you can try on your own to change the center and see how that changes the process. And you'll see sometimes, well, usually actually, the process isn't changed too much. You'll just get kind of a variation of, well, what you would have gotten for the Maclaurin series. So let's take a look at those examples right now. Right, so now for this example, I want to find the Maclaurin series expansions of sine of x and cosine of x. Now, in doing that and finding the c sub n's using derivatives, the pattern's not going to be as obvious as e to the x was. E to the x is like the easiest pattern. But hopefully we'll get an idea. So let's just see by taking derivatives, shall we? So we have first derivative, second derivative, third. We need to go a little far down the line. So I'm going to go to, so let me see, this is the fourth derivative, and then the fifth derivative. I want to do 6, but I don't have too much space. I guess that's okay. So let's see if we can figure out what's going on here and try to develop some pattern after plugging in x equals 0. So derivative of sine is cosine. Good. Derivative of cosine for the second derivative is negative sine. Derivative of sine is cosine, so derivative of negative sine is negative cosine. Derivative of cosine is negative sine, so we have a double negative sign, which is back to positive sine. So basically notice every fourth derivative goes back to the sine. So we can actually look at this, this pattern here and just loop it down. So then it'll be cosine, then negative sine, and so on. Perfect. And now we're going to plug in x equals 0 into these to see if we can see any patterns in the c sub n. So we need f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f 4 primes of 0, fifth derivative evaluated as 0, and sixth derivative evaluated as 0. That's 6, yeah. Good. So now let's see, what do we get? Well, notice sine of 0 is 0. So anything that has a sign will actually go to 0. And that's every other one as it turns out. Cosine of 0 is 1 though. So notice it's positive for these ones and then negative for the one where it's negative. So really we have alternating signs. And you can kind of see that because the next one would be negative cosine, which when you plug in 0 is a negative 1. So the fact that the negative sign comes out for every two derivatives basically, and since every other derivative is going to be sine, those will be 0 when you evaluate them at x equals 0. So that's what this arrow should be labeled as, I guess. Well, notice here, So to kind of like write this in a piecewise way, I guess we can say, c sub n is either 0 or positive 1 or negative 1. But maybe we can write the positive 1, negative 1 as an alternating negative 1, positive 1. So negative 1 to the nth power. So now let's see if this works. So here it's 0 when n is, it looks like even. Because if n is even, then notice what we have here is, well, 0 is even, 2 is even, 4 is even, 6 is even. So the even ones are 0. So if n is even, c sub n is 0. If n is odd, is it negative 1 to the n? I think it's, it is negative 1 to the, well, let me kind of think here. I guess it would technically have to be negative 1 to the, it just sounds kind of funny, but it actually works out. So remember, since we're starting at 0, the first term would be this one. And negative 1 to the 0 is indeed positive 1. So even though this n may not correspond to the original n's we had, we're kind of re-indexing things a little bit. So really what we're going to write for our c sub n's are these ones. So this will be our c1, this will be c2, c3, and so on. And in fact, I've kind of made a slight mistake here because this isn't really c sub n. This is really the nth derivative evaluated at 0. But now from this, we can say c sub n is equal to that divided by n factorial. That we know from Taylor series, or I guess Maclaurin series specifically. Good. So now, well, what happens? What happens is that the only ones that really matter are the odd ones. So the even ones, when n is even, it's just 0 itself. So really what we have is a sum over only the odd terms. So in fact, let me erase this and show that right now. Right, so I've erased, and now let me see if I can try to explain what was going on. So notice we have c sub 0 x to the 0, so that's just c0, plus c1 x to the 1 plus c2 x to the 2. So this is the Maclaurin series expansion of sine of x. I want to go out a few of them, so let's go to there we go, c5x to the 5. That's fine, so kind of ignore that part. All right, so what do we know? We know that when n is even, they're all 0. So this is 0, this is 0, this is 0, and so on. And now what we have is c sub odd numbers. So really what we can do is we can write this as, and also they alternate in sign because of the negative 1 to the n part. So really we can write this as the following. We can write this as the sum from n equals 0 to infinity of, we have negative 1 to the n over, I want to say n factorial, but remember the only existing terms here are the odd ones. So really these n's won't be actually n, it'll be the odd n's. And the odd values of n are actually 2n plus 1, believe it or not. So it's going to be 2n plus 1 factorial. And then times x to the odd powers, which is 2n plus 1. So the real recognition here is that 2n plus 1 means odd, and 2n, I guess, would then be even. And we'll see that with the next example for cosine. That's 2n. Good. And you can see this clearly works because when you plug in 0, what you end up getting is, well, negative 1 to the 0, which is 1. So it starts with positive. And here you will get 1 factorial on the bottom, x to the 1. So we'll actually legitimately get this, kind of what I was describing over here. I know I've kind of written kind of weird. But if you take a look back up before I erase things, the 1, negative 1, 1, negative 1, it was positive, then negative, then positive, then negative, then positive, then negative, and over odd factorials. So this really describes it, and also the powers of x are odd as well. So perfect. And by the way, here the interval of convergence is actually also negative infinity to infinity, and you can definitely check that by ratio test, but I'm going to speak in the language of radius of convergence. So I'll just say the radius of convergence is infinity here. And this is the answer as far as Maclaurin series for sine of x. Okay, so now let's see if we can do the same thing for cosine. I'm going to try to take a little less time on it. But let's see. So we know first derivative, second derivative, third derivative, and we don't need to go beyond the fourth one. Because as we've seen with sine, every fourth derivative of sine or cosine goes back to the original one. So notice here we get negative sine, derivative of that is negative cosine, derivative of negative cosine is double negative sine, which is positive sine, derivative of sine is cosine. So notice we're back indeed to cosine of x. Great. And now when we plug in 0, the sines are all 0, and the cosines are 1. So 1, negative 1, 1. And notice, look, we still have an alternating ones, 1, negative 1, 1, negative, alternating signs of 1s. But here, every other one is 0, with the odds being 0 now. So instead of the evens being 0 like sine, only the even terms are non-zero here. So basically the even terms survive. So we're summing over even terms. So just to make a long story short, similar to what we did over here for part 1 of this example, we'll get that f of x, which is cosine of x, is the sum from n equals 0 to infinity of negative 1 to the n, because it's alternating in sign, only over the even terms now, because the even terms are the ones that are non-zero. So that'll be over an even factorial, so 2n factorial, times x to the 2n. Perfect. And here, the radius of convergence, much like with a sine, is also infinity. And again, you can check that by a ratio test, and it's not too bad. So this is the Maclaurin series expansion for both sine and cosine. Now, a really, really, really nice and kind of deep fact here is, well, Maclaurin and Taylor series expansions, what they do is they basically try to, I guess you can say, approximate a function by a polynomial. We're basically writing it as an infinite polynomial. That's what power series basically are infinite polynomials. So they're kind of like polynomials with infinite degree, really. And notice, if we do that with sine and cosine, well, the real funny thing that happens is that for sine we only have odd powers, and for cosine we only have even powers. Why is that funny? It's funny because sine is an odd function, cosine is an even function. So if you go back to trig identities, and we've seen that before in class, I think, sine of negative x is the same as negative sine of x, and cosine of negative x is the same as cosine of x. So that means that sine and cosine are odd and even, respectively. Which is funny because cosine here is over the even terms and sine is over the odd terms. So literally an odd function, literally an even function, which I think is a pretty nice fact. It kind of like meshes together well. So good. So now we're not done yet. We still have a little bit to discuss. So I'm going to look at some more examples right now. All right, so here I want to find the Maclaurin series expansion for f of x equals 1 plus x all to the kth power. Now when k is an integer, positive integer, you can actually expand this out, and basically that is the Maclaurin series expansion. The only thing is that since it's a finite polynomial, some of the terms would be 0 in the actual infinite Maclaurin series expansion. Maybe we'll take a look at that after the fact, but for right now, let's just see if we can follow suit with the same ideas we saw earlier. So we know f of x is itself 1 plus x to the k. This is like the 0th derivative, if you will. The first derivative, well, a k comes down by power rule, and this is going to be 1 plus x to the k minus 1 now. And then for the second derivative, another, well, the power comes down, so that's k times k minus 1. X plus 1 to the k minus 2 now by power rule. And then I guess we could do one more for the third derivative, and we will get k times k minus 1 times k minus 2, but now times x plus 1 to 1 power less by the power rule, which is k minus 3. And of course this process goes on and on, as we've seen. Now if we let x equal 0 because we want to do Maclaurin series expansion here, well, notice when x is 0, we just have the base being 1, and 1 to any power is 1. So for the first one we get 1, for the second one we get k, then k times k minus 1, and then k times k minus 2. Perfect. And moreover, if we, well, let's just say this, in general, the nth derivative evaluated as 0 divided by n factorial, so I'm just kind of cutting to the chase here as far as our coefficients go, c sub n, is, well, it's going to be k times k minus 1 times k minus 2, and then I guess we have to go up to the second to last one, so kind of think of what's going on here. So this is basically starting a factorial for k, but notice we stop at here k minus 1. This, by the way, should have been k minus 1, k minus 2. I made a mistake there when I wrote that because of these three, okay? Now, like I said, here we stop at 1, k minus 1, but we were at second derivative. Here we stopped at k minus 2, but we were at the third derivative. So here we're going to stop at, well, k minus n, but plus 1, basically. Now, why I say plus 1, even though it would be the one before that, is basically because we're subtracting. So notice that if we were to stop at, let's say 3, we would need to do negative 3 plus 1 would be negative 2. So if you want to say stop at n minus 1, you could say k minus n minus 1 in parentheses, but then after distributing you get this, essentially. And then over n factorial. Okay. Now, I feel a little weird about this notation. The book uses this. But this is what is known as k choose n. Now, this is true when k is a positive integer. So let me say when k is a positive integer. And if you haven't seen k choose n before, basically these are coefficients, well, they're binomial coefficients. So they're basically the entries you would get in something like Pascal's triangle, which is actually really nice. So if you want to explore that, you can, but this is really all I'm going to say as far as this goes. And with that being said, we actually have a Maclaurin series expansion, and it is going to be, well, f of x will be equal to these c sub n, so it's going to be the sum from n equals 0 to infinity of k times k minus 1 times k minus 2 all the way to this over n factorial. But if we take this, if we use this notation for all k, it would be nicer. But I'm just used to using this notation only when we have integers to deal with. But if we take this as being defined as this for all values of k, then I'm okay with using that notation. But just because I already started this, I'm going to go with kind of where I started things out. So that times x to the n. Good. Because again, the center is at 0 for Maclaurin series. All right, so that's it for this one. So this is the Maclaurin series expansion of this. And for what values of x does this converge? So you can actually check, but again, by ratio test, it is definitely true that n factorial will approach infinity faster than the top does for all values of k and x actually. So basically what we end up getting is also an interval convergence of negative infinity to infinity. So really a radius of convergence of infinity. All right, so that's kind of neat. Now the reason why I wanted to go over this is because even though, like I said, this is just really expanding a binomial, it's true for any value of k if you take this binomial coefficient, quote-unquote binomial coefficient, to be this. So actually we can take a look at an example, for instance, when k is equal to 1/2, or in other words, the square root of 1 plus x, stuff like that. I'm not going to do specific examples like that. I think that's a little too much. But this is just something I wanted to show as far as Maclaurin series expansions go. So with that being said, here's what I'm going to do. I'm going to now summarize all of the things we've seen so far in this section, which are, well, e to the x, sine of x, cosine of x, the binomial expansion. I'll also even include things like ln of 1 plus x from 11.9 and tangent of x also from 11.9. And from there, we'll do one example that'll tie everything together and will be a nice conclusion of Calculus 2. So let's take a look at that right now. I'll leave it up to you to figure out the details, but essentially it's a ratio test. It's a little complicated than more than we're used to, but it's not terrible. And the ratio test will actually conclude that the radius of convergence is 1. So this only works when an absolute value of x is less than 1. Now, as far as testing the endpoints go, that depends on the value of k as it turns out. So yeah, that's kind of all I wanted to say as far as this binomial function goes. Now it's kind of interesting because again, when k is an integer, a lot of these terms will be 0 because it'll just be a finite sum. But if k is not an integer, like let's say 1/2, then, well, this is really the square root of 1 plus x. And, well, then you can actually find out the Maclaurin series expansion from there using this. So that's kind of nice. Now, I'm not going to do a specific example like that. I feel that that's too much. But here's what I am going to do, though. So now what I'm going to do is I'm going to summarize what we've discussed so far. So I'm going to include all the Maclaurin series expansions we've seen, e to the x, sine of x, cosine of x, the binomial function here, 1 plus x to the k. I'll also include things like ln of 1 plus x from 11.9 and tangent inverse of x from 11.9. I feel those are pretty useful as well to see. And from there, we'll do an example that'll be a nice conclusion of Calculus 2, and I'll tie all of these topics in together. And let's take a look at that right now. Right, so here's the list I was talking about of all the Maclaurin series that we've seen in this section and in the previous section. These two in particular are from the previous section. Well, actually this one as well, of course. Along with the radii of convergence, which I think is kind of nice. Yeah, so now what I'm going to do is I'm going to take a look at this nice example here. It's two parts. So first I'm going to evaluate this integral as an infinite series, and then I'm going to find this limit. And we're basically using infinite series here. We're using Maclaurin series. And in fact, since they're all involving e to the x, I'm going to basically be spamming this Maclaurin series expansion of e to the x. Now this one's going to be a little different because e to the negative x squared. So notice e to the negative x squared using Maclaurin series expansion is just replacing the x in the expansion with negative x squared. So this is the sum from n equals 0 to infinity of, well, negative x squared to the n over n factorial. Now notice negative x squared to the n, we've actually seen this before. We can split it up in such a way that we can write this as negative 1 to the n times x to the 2n. So that we can see that it's clearly an alternating series. Good. And if we wanted to integrate both sides with respect to x, let me just make a little bit of space here to show that. There we go, we get this. And we know that everything's a constant except for x to the 2n. So really we can pass the integral through. So we get kind of like this image here. Negative 1 to the n over n factorial. But then integral x to the 2n dx. Because everything else is a constant with respect to x up to x to the 2n. So basically you can pull those out of the integral. And pass the integral through the sum because of, well, from what we saw from 11.9. So now, antiderivative of x to the 2n is x to the 2n plus 1 over 2n plus 1. So the 2n plus 1 in the denominator joins this n factorial in the denominator, and we end up with this. And it's alternating, good, and it's the sum from n equals 0 to infinity. And if you want to write a few terms out, we certainly can. Let's see if we can just do it real quick. Also, I guess I should say this is plus c, technically, and I think that makes sense because again, this is a indefinite integral. So for an indefinite integral, you'll always have plus c at the end. But again, let's write down a few terms. So when n is equal to 0, notice that the odd terms will start at 1, and 0 factorial is 1, and negative 1 to the n is positive. So basically what we get for our first term is 1. Minus, because it's alternating, x to the, well, you know what, it's actually x to the 1 for the first term, so it's really x, there we go. Minus x to the third over 1 factorial, which is 1 times 3, plus x to the fifth over, now we're at, let's see, so it's 0, 1, now we're at 2 factorial. 2 factorial is 2. 2 times 5 would be 10, and then minus and so on. And then plus c. So that's kind of nice that we can see it like that, but I'm gonna box this because I like the compact forms better. But yeah, you can always write them out. I should include this plus c in our box. Okay. Now for the next problem here with this limit, to be quite honest, we can do this by L'Hopital's rule, but I want to showcase, obviously, the use of Maclaurin series here. So remember, e to the x is the sum, and we'll actually write it out. So it's going to be, when we plug in 0, we get x to the 0 over 0 factorial, which is 1, plus x over 1 factorial, which is just x, plus x squared over 2, plus x to the third over 3 factorial, and then it goes on and on and on from there. And then we have this minus 1 and minus x. So notice, since we're subtracting 1 and subtracting x, I don't know if we can quite make it out, but I'm going to have to tilt things a little bit here for us to see that. So I'm going to do minus 1 minus x in the numerator from this minus 1 minus x here. And notice what happens in the numerator. There we go, it's all over x squared. Now what happens in the numerator, of course, is that the 1 and x cancel out each. Just like that. There we go. And now all we have left in the top, well, it's x squared over 2 plus x cubed over 6. And I stopped there, but really there should be a plus, dot, dot, dot. And since we're dividing by x squared, we're really multiplying this whole thing by 1 over x squared and then taking the limit as x goes to 0. So now if you distribute this in, what we end up getting is a limit as x goes to 0 of, for the first one, you just get 1/2. Plus, for the second one, we get x over 6. Plus, it would be x squared over 4 factorial, which is 24, and so on. But the whole point is that all of these terms beyond 1/2 will all include an x. Specifically, what I'm trying to say is they'll all go to 0 in the limit because we're letting x tend to 0. So in fact, the answer here is just 1/2. And you can use similar ideas for other limits involving, let's say, sine or cosine or even tangent inverse. So that's kind of nice, but to be quite honest, L'Hopital's rule kind of trumps that as far as limit tools go. But for evaluating integrals that are otherwise not integrable, power series, or I guess Maclaurin series in this case, is definitely the way to go. And in fact, let me just say, if we had a definite integral, let's say from 0 to 1, then you would let x be 1, minus let x be 0. It would all be 0 though, because it would be, well, a sum of zeros. So that'd be kind of interesting to take a look at, but it's really just this when x is 1. So that's kind of nice. But yeah, that concludes 11.10, and it concludes Calculus 2. So I really hope you enjoyed the class. I really hope you enjoyed the video, and I guess I'll just see you around. Thanks for watching.